The antenna never opened. 3 ribs stayed locked in place, leaving Galileo's giant umbrella-shaped dish half-folded as it drifted away from Earth. That single mechanical failure stayed with the spacecraft all the way to Jupiter. Instead of sending discoveries home at the speed engineers had planned, Galileo would spend the rest of its life whispering through a much smaller antenna, forcing every valuable observation onto an aging tape recorder before the data could crawl back across the solar system. Years later, that crippled spacecraft would become the reason scientists began looking at Europa very differently. The disappointment arrived long before Jupiter filled the sky. During the cruise to the outer planets, engineers watched telemetry confirm that the high-gain antenna had failed to deploy correctly. Months of attempts to free it accomplished nothing. The spacecraft still functioned, but one of its most important systems never came online. Planned transmission speeds collapsed from more than 100,000 bits per second to rates that could fall into the double digits. That changed almost everything. Every detailed photograph, every magnetic measurement, every scientific record gathered during a close encounter first had to survive inside Galileo itself. Only afterward could those files trickle home through the low-gain antenna, sometimes taking months of continuous tracking by NASA's Deep Space Network. The mission was still alive, but it would operate with a permanent handicap. Deep inside the spacecraft, another piece of hardware quietly became indispensable. The digital tape recorder. Originally intended as temporary storage, it suddenly became the only practical way to preserve large volumes of scientific data. Every close flyby depended on magnetic tape wrapped around delicate reels buried inside the spacecraft. Without it, Europa could be photographed, measured, and mapped, but none of those observations would ever reach Earth. Then another setback appeared. Just before Galileo entered orbit around Jupiter, the recorder unexpectedly raced forward for roughly 15 hours. The tape stretched and suffered damage. Engineers could not replace it. They could only work around the injured section by rewriting operating procedures and carefully controlling how the mechanism moved. The recorder survived. Just barely. Its remaining capacity became one of the mission's most valuable resources. Far ahead, Jupiter's enormous magnetic field waited. The planet does not simply possess radiation. It traps extraordinary numbers of high-energy particles, creating one of the harshest radiation environments anywhere in the solar system. Every trip toward Europa carried Galileo deeper into that invisible storm. The spacecraft had been designed for a certain amount of punishment. By the end of the mission, it had absorbed more than 4 times that amount. Radiation did not damage the spacecraft all at once. It accumulated. Electronics slowly became less reliable. Sensors grew noisier. Memory bits occasionally flipped without warning. Instruments that had behaved predictably for years began acting differently after repeated passages through Jupiter's radiation belts. At first, the degradation seemed manageable. Eventually, it did not. As Galileo's original mission approached its planned conclusion, many expected its useful life to be nearly over. Instead, NASA approved an extended campaign focused heavily on Europa. That decision raised the stakes. Each new flyby promised more valuable science. Each one also increased the chance that the spacecraft might never recover. Engineers could not simply wait for trouble and respond. Commands required hours to cross the enormous distance between Earth and Jupiter. During a Europa encounter, Galileo was effectively on its own. If radiation forced the spacecraft into a protective shutdown at the wrong moment, nobody on Earth could intervene before the opportunity was gone. Everything depended on the onboard systems continuing to function. One close approach after another carried Galileo to within about 1,000 kilometers of Europa's frozen surface. The view changed. Long fractures stretched across the ice. Broken regions looked as though enormous plates had shifted and frozen again. The camera recorded landscapes unlike those on any other known world, although increasing radiation damage scattered bright defects across many images. Engineers later filtered much of that electronic noise, separating genuine terrain from artifacts created inside the detector. The photographs revealed an unfamiliar landscape, but they were not the mission's most important result. Elsewhere aboard the spacecraft, a long boom carried an instrument that did not rely on dramatic images. It measured magnetic fields. As Galileo swept past Europa during several key flybys, that instrument recorded something unexpected. The surrounding magnetic field did not behave exactly as Jupiter alone should have produced. The field lines bent. They shifted in rhythm with Jupiter's rotating magnetic environment. The pattern appeared again. Solid ice could not explain it. A highly conductive layer could. The measurements pointed toward an induced magnetic field generated inside Europa itself. The simplest explanation was a vast global layer of salty liquid water beneath the frozen crust. Galileo had not found life. It had not photographed an underground ocean. The magnetometer had revealed evidence that something electrically conductive, consistent with a deep saltwater ocean, existed beneath the ice. That changed the question scientists were asking. Europa was no longer simply another frozen moon orbiting Jupiter. It became one of the solar system's leading candidates in the search for environments where life might exist. Meanwhile, the spacecraft continued to weaken. Radiation-triggered computer resets interrupted operations. False signals appeared. Sensitive instruments occasionally shut themselves down near critical observations. The star tracker sometimes mistook radiation effects for real stars. Even routine operations demanded increasingly careful planning because no one knew whether the next burst of energetic particles would strike a vulnerable circuit at exactly the wrong moment. Yet Galileo kept returning. Its capabilities continued to decline, while the scientific value of each successful observation kept rising. A spacecraft expected to fade quietly after its primary mission instead produced some of its most influential discoveries while operating far beyond the conditions it had originally been built to endure. Eventually, there was only one acceptable ending. If Europa truly possessed a global ocean beneath its ice, planetary protection became far more important. An aging spacecraft carrying terrestrial material could never be allowed to crash accidentally onto that surface. The destination Galileo had helped redefine now had to be protected from its own visitor. On the 21st of September 2003, final commands guided the spacecraft into Jupiter's atmosphere. It entered at nearly 48 kilometers per second. No recovery was possible. The spacecraft disappeared beneath the clouds of the giant planet it had studied for years. The broken antenna never unfolded. The damaged tape recorder never stored another observation. The magnetometer stopped tracing invisible lines through Jupiter's magnetic field. Europa remained behind, orbiting in silence beneath its shell of ice, while measurements returned by a spacecraft that refused to fail, on schedule, continued guiding scientists toward the hidden ocean below.